And next up, problem 2, multiplying rational expressions. Let's take note of what it says at the top. You can use what you know about simplifying rational expressions when you multiply and divide them. So what is the product? X squared plus x minus 6 over x minus 5 times x squared minus 25, difference of squares, over x squared plus 4x plus 3 in simplest form. State any restrictions on the variable. Beginning with the multiplication and factoring where possible, we find some common binomials that we can cross-reduce. And this is very much like cross-reducing fractions in the past. That goes back to the key idea or concept that was discussed earlier. A lot of what we know about multiplying and dividing fractions still applies when we're multiplying and dividing fractions that are a little bit more complicated. These fractional expressions with polynomial numerators and polynomial denominators. So again, here we've got the x minus 5 canceling with the x minus 5. That's a cross reduction. Same thing with the x plus 3. Cross reducing, we get the two binomials you see over the binomial denominator. Restrictions though. We also have to mention the restrictions. So looking back to the factored forms of these expressions, we note any x values that would lead to a denominator of 0 in either expression. So I'm seeing x equals 5 would give us a 0 denominator, as would x equals negative 3 and x equals negative 1. So those are all exclusions from our domain for our product. And it's that time again, another chance to show that you have got it. What is this product? In simplest form, make sure you state any restrictions on the variable. Work carefully and make your selection from the choices below. Example problem number 3, dividing rational expressions. Oh, that sounds so difficult. That's really not. Just like dividing other fractions, all that we are going to do is reciprocate or flip the second fraction and multiply. So it becomes a multiplication problem, very similar to example problem number 2, where we factor, cross-reduce, and simplify. Here are the steps, what you should think on the left, what you should write on the right. I'm going to breeze through this because it's going to be so much like a multiplication problem once we invert the second fraction. Flip and multiply. You may walk through the steps, pause the video, read through it, make sure you understand. But I assume if you understood example problem number 2 and you remember how to divide fractions, you will have no trouble with this, apart from making sure, as you did when multiplying expressions like this, to identify the restrictions on the domain. And another opportunity to show that you have got it. Please read this question yourself. Work carefully and make your selection from the choices below. Question 2 of 2. So we haven't seen an example like this, but we've learned some logic, some basic fundamentals of completing problems like this. What do you think? Without doing the calculation, what is the greatest number of restrictions the quotient could have? I'll let you read the quotient and explain. Please don't work carefully. If you would, just blindly choose A, B, C, or D. I'd go with C. Example problem number 4. Using some of this math to do real stuff. So here we go. That's not quite what it says, but close enough. Construction. Your community is building a park. It wants to fence in a play space for toddlers. They might crawl away. It wants the maximum area for a given amount of fencing. Maximum area for a given amount of fencing, which would be the perimeter. Which shape, a square or a circle, provides more efficient use of the fencing? Neat question. I thought it was going to be a square or a non-square rectangle, and that's pretty easy, and a lot of you have probably seen problems like that in the past. But a square versus a circle, that's a good one to consider. One measure of efficiency is the ratio of area fenced to fencing used, which is just really area to perimeter. Which of the two shapes has the greatest ratio? So what we need to consider are the area and perimeter of both squares and circles. So let's begin with squares. Our s squared, well, let's just start back up here. S equals p over 4. Area over perimeter then will equal the area, which is side length squared, over p, perimeter. And then to solve, well, p over 4 squared right? That's just our equivalent value for s. We rewrote s as p over 4, so now we're substituting. P over 4 squared would equal, remember that 2 would get distributed to both the numerator and denominator, so that becomes p squared over 4 squared, or p squared over 16. And then that p squared over 16 is being divided by p. So that's a 3-story fraction, is what that's called. And you can see why we have 1, 2, 3 stories, and it's a fraction. But if we think of the denominator as being its own fraction and rewrite p over 1, now we have a 4-story fraction, and that's really just a division problem of 2 fractions. So think of this instead as being p squared over 16 divided by p over 1. You then, of course, would invert and multiply, cross-reducing the p squared with the p in the denominator. So you'd have p over 16 when you simplified. So that's the ratio we're going to compare to the circle here. Circle's area pi r squared and its perimeter 2 pi r. Again, we'll rewrite r in terms of the variable p, so radius equals perimeter over 2 pi. And keep in mind the reason for doing that is we're going to be looking to substitute p over 2 pi for r in our expression in just a moment. Area over perimeter is pi r squared over p, but here we substitute p over 2 pi for r. Simplify, very similar to when we simplified for the square just a moment ago. And now we find p over 4 pi to compare to p over 16. So now we're looking to figure out whether p over 4 pi is greater than, and it tells us right below, but if we were on our own, we'd be looking to determine whether 4 pi is greater than, less than, or potentially even equal to 16. Since 4 pi, approximate pi is 3.14, 12, 13, 4, it is, 4 pi is less than 16. Thinking about what that does to the fraction with the common numerator of p, that makes the fraction greater. Right? Smaller denominator, greater fraction, assuming numerators are equivalent. So there we go. P over 4 pi is greater than p over 16, so a circle provides a more efficient use of fencing. Interesting. And we can check that. Assume that p equals 40 feet. We plug in a value, a concrete value. Not that we're using concrete fencing. I'm talking about a static number. Oh, not like static electricity. Static is in not dynamic. Static is in stays the same. It's a concrete value, not a variable. Plug in 40 and just ensure that it works, that truly a circle would have the, let me just read this. Assume p equals 40 feet. The area of the circle is pi times 40 over 2 pi squared. That's about 127 square feet. With the square, we get about, well, we get exactly 100 square feet. So using the same number of, or same amount of fencing, we get greater area with the circle. Go figure. Plus, with the circle, there are no corners for the kids to get stuck in. And that moment you've been waiting for, the chance to show that you've got it. Remember, circular fences. Babies don't get stuck in corners. Construction problem. Which shape of play space, sounds familiar, provides for a more efficient use of fencing? A square or an equilateral triangle? Hint. The area of an equilateral triangle in terms of one side is 1/2 s times the square root of 3 over 2 times s. Of course, s represents the side length of the triangle, and because it's an equilateral triangle, all 3 sides are the same length. So you'll complete this work very similar to the example problem. We're also told the perimeter of an equilateral triangle is 3s. That seems silly. We could have figured that out on our own, whereas the formula for finding the area is a little bit more obscure, but perimeter, that's just side plus side plus side. Anyhow, you have 2 choices below. So work fast and take chances. And finally, your lesson check. Problems 1 and 2. If you'd like, now's your chance to pause. Questions 3 and 4. Pause now or forever hold your... And finally, 5, 6, and 7. You must have a slave driver for a math teacher assigning you 7 problems.